continuity. In this lesson, we are going to learn the continuity of a function f of x at a point A, and also the continuity of a function given by a graph or by a formula, or continuity of function on an interval, and also we're going to talk about removable discontinuities. Now, a function f is continuous at a point A if its graph has no hole, no jump, or no break at that point. Now, if you look at this function, here's a function given by a graph. You can see this function is not continuous at -4. So it's not continuous at x equal to -4 or at -4 because it has a hole. And it is not continuous at -2 at x equal to -2. It is not continuous because it has a break. And also it's not continuous at 1. At 1, what it has is again a hole. And at 4, again it's not continuous because it has a jump. So this function is not continuous at 4 places. At -4, there is a hole. At -2, there is a break. We call it infinite discontinuity on this one. Infinite discontinuity. Infinite discontinuity. And x equals to 1, there is a hole here. And at 4, there is a jump. And this function is continuous everywhere except these two, the 4 places. Therefore, the function is continuous on the interval from -infinity to -4. And then from -4 to -2, it is continuous. And then from -2 to 1, it's continuous. Or from 1 to 4, it's continuous. And then from 4 to infinity, it is continuous. So the function is continuous on these intervals. Now let's look at the definition of continuity of a function at a point called A. A function f is continuous at A if limit x goes to a f of x is equal to f of a. So basically a function is continuous if the limit is same as the value of the function at that point. This actually has 3 conditions in it. First one is f of a exists. Second one is the limit x goes to a f of x exists. Limit x approaches a f of x exists. And the third condition is the limit x approaches a f of x is same as f of a. Now let's look at the example that we had here. Why this function is not continuous at, say, -4. This is not continuous at -4 because f of -4 does not exist. Because we have a hole here, mean we don't have f of -4. So that means f of -4 does not exist. Now what is the reason that is not continuous at -2? Both the first conditions violated. F of -4 does not exist. And the limit x approaches -2, f of x does not exist. because the left limit goes to positive infinity and the right limit goes to infinity. Even infinity we call normally does not exist. And then that is not continuous at 1 because we have f of 1. What is f of 1? F of 1 is this point, which is 3. We have f of 1. Also, the limit x goes to 1, f of x exists. As x approaches 1, that f of x approaches negative 1. So it actually violates the third condition, where third condition is what? The limit x approaches 1, f of x is not equal to f of 1, the third condition. So that is the reason that it is not continuous at that point. Now at 4, why at 4 it is not continuous? F of 4 exists. F of 4 is equal to negative 1. It is not continuous because the limit x approaches 4, f of x does not exist. The left limit is negative 1, the right limit is 2, so the limit does not exist. So that is the reason that is not continuous at 4. Removable discontinuity. If the discontinuity is because of a hole in the graph, such as at negative 4 or at 1, we call it a removable discontinuity. So we have a removable discontinuity at negative 4 and at 1. At removable discontinuities, the limit exists. The limit x goes to a, f of x exists. The problem is either f of a does not exist or the limit is not equal to f of a. So at removable discontinuity, we limit exists and discontinuity occur because either f of a is not defined or the limit and the function value are not the same. Now you can see at negative 4, the limit exists. The limit as x approaches negative 4, f of x, as x approaches negative 4, f of x approaches 2. So the limit exists. Here this is the removable discontinuity because f of negative 4 does not exist. And also in this situation you can see the limit exists. A limit as x approaches 1, f of x is negative 1. Example number 1. Is f of x continuous at x equals to 2? We want to know whether this is continuous at x equals to 2. So we need to go to the definition. So we need to first find f of 2 and we need to find the limit as x approaches 2 of f of x, and then we want to see whether they are the same. If they are the same, then it is continuous at 2. If they exist and they are the same, that is continuous. Otherwise it is not continuous. Now what we see, f of 2 in this one, the value of the function when x equals to 2 is equal to 1. And the limit as x approaches 2, not at 2, as x approaches 2. So we have to use this part because this part is, so if you draw the number line, this is 2. This part is, well, the values below 2 and also for the values above 2. So that is what this function is. So as x approaches 2, that function we want to find. So you can see if I substitute 2, what I get, 0 divided by 0. So clearly we have to use the algebra. So that means we get a limit x approaches 2. The numerator I can factor x minus 2 and x plus 1. Factoring is easier because what we have to guess is the x minus 2 has to be a factor if you want to simplify this. So this is a factor. And then this cancels out. So we want to know as limit x approaches 2x plus 1, it approaches 3. So clearly it violates the third conditions. So f of 2 exists, which is 1. The limit exists, which is 3. The problem is the limit x approaches to f of x is not equal to f of 2. So therefore it is not continuous. Not continuous at 2. Not continuous at 2. So if you graph this situation, this one, what you're going to see is a hole at x equal to 2, you will see a hole in the graph.